taking a look at electronegativity and bond polarity. Electronegativity comes from the idea that we know that the nucleus is a positive entity and it attracts electrons that are circling it in some way, shape, or form that are negative. This positive and negative attraction keeps electrons near the center or the nucleus of an atom. Electronegativity, which I abbreviate as EN pretty much everywhere, is the measure of an element's atom's ability to attract shared electrons in a bond. So a larger electronegativity means a greater attraction to electrons. If we looked at something like potassium with chlorine, we know that potassium is a metal, chlorine's a nonmetal. We have an ionic bond being formed here. That means there's a full transfer of electrons. So what you need to know at this point, we're going to get to it, is that potassium has a really low electronegativity and chlorine has a pretty high electronegativity. So a larger electronegativity means a greater attraction to electrons. We would be able to draw something like this for the electron dot diagram. And remember, it's these two electrons here that would be involved in bonding because they're unpaired. So in an ionic compound, we know that there's a full transfer of electrons. There's a full transfer because potassium with chlorine doesn't really want to hold on to its electrons, whereas chlorine, when it's with potassium, really wants to take those electrons. So electronegativity just describes something we already know that occurs. The potassium gives up its electron to become potassium positive, and chlorine steals potassium's electron to become negative. This transfer of electrons was, of course, known, but we could relate it back to this idea of electronegativity. All right, let's take a look at the electronegativity values on our periodic table. Electronegativity, if you're looking at the key at the top of your periodic table with iron, electronegativity is listed below the atomic number. So we can have electronegativity values from 4 all the way down to something fairly low, maybe 0.7. So this is considered a low value. This is considered a high electronegativity. So let's describe the trend in electronegativity on this periodic table. Let's look at two things as we move from left to right across our periodic table and as we move top to bottom. So as we move from left to right across our periodic table, let's look at the second period here. So lithium has an electronegativity of 1, beryllium is 1.6, boron is 2, then we have 2.6, 3, 3.4, 4. So we could say that electronegativity increases, across the periods of our periodic table. It may not be as evident, however, in general, it will be increasing. So let's go to period 5, for instance. We have 0.8, 1, 1.2, 1.3, 1.6, 2.2, 2.1, 2.2, 2.3. So it kind of fluctuates a little bit. But in general, we could say that the electronegativity increases from rubidium all the way over to iodine. As we go down the periodic table, so down a group, let's look at our first group and then maybe we'll scoot on over to group 16. So group 1, remember hydrogen is a nonmetal, so we don't really get to classify it with these. So let's start at lithium. So actually, I guess we could classify it in this case, but it follows the trend where we have 2.2, 1, 0.9, 0.8, 0.8, 0.8, 0.7. So in general, electronegativity decreases as we go down a row or column, sorry. Let's go over group 17. We have 4, 3.2, 3, 2.7, and 2.2. That still follows that general trend. Describe the periodic trend for atomic size or radius of the atoms on the periodic table. And we're going to go again from left to right and top to bottom, just to have similar comparisons. So let's do from top to bottom first. It's something that we are quite familiar with. So if I were to draw the full electron dot diagram for lithium versus potassium or rubidium. So lithium has 2 electron levels. Of course, our first one is full and the second one only has 1 electron. If we looked at rubidium, for instance, next, I'm just going to give myself some room here. Rubidium has 1, 2, 3, 4, 5 levels. Oh my goodness, why did I commit to drawing so many? 1, 2, 3, 4, 5. Already, I'm really hoping you're getting a sense of what's happening here. All of these levels will be full of electrons. And this last one has 1 electron. What do we notice about the size between lithium and rubidium? If I were to have drawn perfectly circular, same size for the first 2 levels, well, we would notice that rubidium is bigger. Rubidium is bigger because as we go down the periodic table, there are more orbitals further from the nucleus. So radius increases. So I'll note that here, radius increases as we move down the periodic table. So if we compared that back to electronegativity decreases as the radius increases, meaning rubidium doesn't hold on to this electron as well as lithium holds on to this electron. Rubidium is more likely to give up their electron than lithium when combined with maybe the same other nonmetal. Okay, so it looks like electronegativity and radius might be opposite of one another. Okay, so if electronegativity is increasing here, we should expect radius to be decreasing. Now, this is actually the case, and it seems a little bit counterintuitive, and it's tricky for students often. So let's compare an element like lithium and oxygen. So again, we're going to draw lithium. I'm going to do it a little bit bigger this time. And oxygen. I want to try and make them the same size just so that it looks similar for everybody. Okay, and this was oxygen, which looks confusing. All right. Now, we know that these have the same number of orbitals or levels for electrons within the same row across. However, oxygen has more electrons than lithium does. Okay, so lithium has 3 total electrons, whereas oxygen has 8 total electrons. Now, if you were to look at lithium has how many protons? Well, it has 3 protons, so 3 positives right in the middle of it. Okay, so right here we'd have 3 positives. In the middle of oxygen, we have how many protons? Well, we have 8 protons, so 8 positives. Because there are more positives here, they can have a stronger pull on any of our valence electrons than our 3+ pull. Okay, so this has a stronger attraction to electrons around it because it has more protons in nucleus. So therefore, these electrons in oxygen are pulled in tighter than the electrons surrounding lithium. So the radius decreases. This seems a little bit weird. Again, it's just attraction. So you could think about this attraction as a magnetic attraction. We have a weaker magnet and a stronger magnet in oxygen. So oxygen is able to pull its electrons in a little bit more. So radius decreases as we go across the periodic table. If I were to draw a really basic periodic table, I would have something like this. And I could say that the most electronegative element is here, and the least electronegative element is here. if I were taking those two pieces of information and then also relating it to radius, the smallest radius is up here, and the largest radius is down here. So electronegativity and the size or radius of an atom are opposite. If it has a large electronegativity, it has a low radius or small radius, and if it has a low electronegativity, it has a large radius. So these must be inherently related. This is as far as we'll explore that, but you should know the trend for each. Okay, let's get to bonds with polarity and electronegativity. So the electronegativity values are identical for each element in a diatomic. Again, a diatomic would be something like H2, Cl2, O2, Br2, where one element is bonded to its identical other element. Okay, so the electronegativity values for each element in the bond are identical, so they share these bonding electrons equally. Let's take a look. So chlorine, I'm going to draw chlorine like this, just so what's going on. Remember, these two electrons here are between the two being shared to create full octets for each chlorine. Now, if we looked at the electronegativity value for chlorine, chlorine has an electronegativity of 3.2. So if that's the case, nobody has a higher or lower electronegativity value than the other. This means that these electrons are shared equally. It's hard to understand without a comparison to being shared unequally. But what this means is that they are the same distance from each atom. If they're sharing these electrons equally, nobody feels like they have more or less electrons than their original 7 valence electrons. Okay, so if that's the case, they don't have polarity. All right, I'm going to explain polarity a little bit more when we talk about something that is polar, but these are non-polar bond because they are being shared equally. Electrons are shared equally. It can also be said to have no dipole moment. Dipole means two poles, like the north and the south pole. In our case, we're going to be talking about a positive and a negative pole in the end. Okay, so non-polar bond. Each of these electrons that are being shared in the middle, these are the ones we're talking about, they are being shared equally between these two atoms. This happens anytime they have the same electronegativity value. So let's take a look at an example where we have a polar covalent bond. So we'll just start with an example where we have H and Cl. And again, I'm going to draw it like this to begin with. And we'll put their electrons as being nicely shared in the middle between the two of them. Let's find the electronegativity. So we found electronegativity for chlorine last time. It was 3.2. And for hydrogen, looking under its atomic number, you see that hydrogen has an electronegativity of 2.2. So this means that chlorine is more electronegative. That tells us that chlorine likes these shared electrons more than hydrogen does. So it's going to start pulling them towards itself. So if I try and redraw this pretty much the same way, but now I can draw these electrons as a little bit closer to chlorine than they are to hydrogen. Okay, they are still being shared. They're just a little bit closer to one atom than they are to the other. Okay, so if this is the case, chlorine starts to act like it's got a full octet. If chlorine had a very full octet and it owned this blue electron, it would feel negative. But because it doesn't totally own that electron. It's still sharing, just not very nicely. We say that it is partially negative. To denote the partial, instead of just a full negative, I put this funny little Greek symbol. All right, now let's look at hydrogen. Hydrogen appears to have no electrons around it. Now we know again it's still sharing. Okay, there are still shared electrons. However, they're just a little bit further away from hydrogen than it's used to. So hydrogen starts to feel like it's given away its electron. It's not totally given away, it's only partially given away. So it says that it is partially positive. Okay. So these partials tell us that there is polarity happening within our bond. Polarity happens when there is a positive and a negative across a bond. So we can draw this one other way. We can draw H to Cl. And you can, again, you could put in your partial positives or partial negatives, but you can also draw a bond polarity arrow. Okay, and the arrow just shows which way the electrons have moved within this shared bond here. Remember, the line represents two shared electrons. All right, so this is one of two ways you can represent things. You can represent with a partial negative and partial positive, or you can represent with an arrow. And the arrow is always pointing towards the more electronegative atom. Another way I like to think of it is it always gets this little cross put on the end. And I remember that as the partially positive end. So I guess perhaps if I were being really particular here, I would just switch these so that it looks the same in both of my representations. So this would be my partially negative and this is the partially positive for this representation. Again, you can pick one or the other. You don't have to use both. So, because this just explains everything we just went through. So because chlorine is more electronegative than hydrogen, the chlorine attracts the electrons more strongly than hydrogen. The shared electrons between them are held a little bit closer to chlorine than hydrogen in this case. This leaves the end of the bond near hydrogen slightly positive and the end of the bond near chlorine slightly negative. A polar covalent bond is one that we just noted there. It's a bond that has unequal sharing of the electrons, the shared electrons, denoted by those partials. To show bond polarity, we either use a partial, so the partial positive, partial negative, or we use that polarity arrow. Now, how does electronegativity relate to ionic bonds? I kind of showed this example at the beginning, but I'll do it again. Metals have a low electronegativity and nonmetals have a high electronegativity. So let's look at sodium chloride. So sodium and chlorine. Remember, chlorine has an electronegativity of 3.2 and sodium has an electronegativity of 0.9. So the difference between these are a lot greater than the electronegativity difference between, let's say, H and Cl. In HCl, the electronegativity difference, again, a triangle means difference in electronegativity, was 1. In this case, let's take a look at our electronegativity difference. 3.2 take away 1.9 is 2.3. So a much bigger difference in these values between the two elements. Remember, typically we would think of them as sharing. Now, this is incorrect. We know it's incorrect for this diagram, but I'm going to draw it anyways for just a second to prove our point. Okay, so we like to think that electrons are shared equally to begin with in the middle of these two elements. However, because chlorine loves electrons based on its electronegativity, and sodium doesn't really have a really strong electronegativity to hold on to its electrons, sodium ends up transferring its electron completely to chlorine. So it just lets go of its electron. When that happens, it's not being partially positive or partially negative. This is where we have full positives and full negatives because there is a full transfer, of electrons. They're not sharing at all. Okay, so metals have a low electronegativity, non-metals have a high electronegativity. Metals do not attract electrons very strongly in a bond, whereas the non-metals do. So non-metals are going to steal. So we know that metals donate their electrons, non-metals accept electrons, and the ions are attracted to form an ionic bond. So this attraction to shared electrons was so strong for chlorine and so weak for sodium that when these two elements come together, there's a full transfer of electrons instead of sharing. All right, the bonding continuum. The difference in electronegativity across a bond determines the characteristics of the bond. So again, a difference in electronegativity is represented by delta En. So we saw that in a diatomic, the difference between those two same elements would be 0. In a polar covalent bond, it was like a moderately low number. And in an ionic bond, the number starts to increase. The change in electronegativity difference across a bond tells the nature of the bond. It's always positive. So let's just quickly draw the bonding continuum and we'll show the cutoffs. So the bonding continuum can have a few different electronegativity values. If we have a difference in electronegativity between two elements of 0, we know that this is a non-polar covalent bond. Covalent because they are still sharing their electrons equally. Some examples were diatomics, but there's a couple other on your periodic table. For instance, phosphorus to hydrogen. Phosphorus and hydrogen both have an electronegativity of 2.2. So when they bond together, they have a non-polar covalent bond. We also have N and Br. Nitrogen has a electronegativity of 3, and so does bromine. There's lots of other examples of this, but remember, we're looking at covalent, so they had to be two nonmetals. All right, we can go all the way up to a difference in electronegativity of 1.7. In between 0 and 1.7, we call this a polar covalent bond. Polar because there's uneven sharing of electrons. Covalent, again, because they are sharing. So uneven sharing of electrons. Some examples here could be carbon to hydrogen. Carbon is 2.6, hydrogen is 2.2. There's a difference in electronegativity of 0.4. So although that's fairly low, it's still part of the polar covalent bond. So it's not very polar covalent bond. Sometimes it's referenced as slightly polar covalent, but in general, we would say it is just polar. We could also go to HBr. That has a difference of 0.8. It is still polar covalent. All right, now I'm going to add one other example here that's still polar covalent. HF. Now, if we looked at HF, fluorine has an electronegativity of 4.0. Hydrogen is 2.2. So the difference here is 1.8. So technically that puts it just outside this polar covalent, which would start to become above 1.7, it's ionic. However, it seems like it should be ionic, but what we know of a definition of ionic is a metal and a nonmetal and a full transfer of electrons. H is a nonmetal and F is a nonmetal. So this is still covalent bond. It's just extremely polar covalent and teetering on the edge here. So this area around 1.7 can be broken. Okay, there's a lot of other examples we could look at that would fall within here, like lead iodide. So we would look, in this case, we're just looking between lead and iodine. Lead is 1.8 and iodine is 2.7. The difference here is 0.9. Well, that puts it way lower than the 1.7. However, I know that lead is a metal and iodine is a nonmetal. Therefore, when I classify it, this is still an ionic bond. So is the bonding continuum perfect? Absolutely not. It really starts to break the rules for our ionic compounds. However, it is really helpful for remembering the difference between polar covalent and non-polar covalent. So covalent, again, being two non-metals. This is where it's very helpful. There is some practice questions in your textbook, and I would recommend taking a look at those.